When you wake up in the morning, the first thing that you probably do is prepare your coffee. Now, if you've ever prepared your coffee without stirring it, what you might see would be coffee tracks that look like this. Now, this is an example of a Brownian motion trajectory, and it is inherent in solid probe, liquid medium systems. Now, Brownian motion, in a word, is random. It's unpredictable. But despite its randomness, we actually know a lot about Brownian motion theory, so much so that experimenters are using this as an analysis technique. And if, for example, our experimenter is interested in a certain microscopic probe medium systems, they could use Brownian motion analysis to measure D and alpha to learn more about that system of interest. So what is D and alpha, and what do they tell us? D and alpha are the diffusion coefficient and the anomalous exponent, respectively. The diffusion coefficient tells us the speed of the diffusion, while the anomalous exponent tells us the type of diffusion. And there are three types. You have normal diffusion, sub, and super diffusion. Now, normal diffusion is what we see if we have a simple probe in a simple medium. But if there is some sort of complexity in your system, what you might be seeing is anomalous diffusion, also known as scaled Brownian motion. So let's go to a very specific system of interest, the motion of proteins in cells, which are known to be subdiffusive. Now, cellular biologists are asking why? And the most common arguments are the following. One, you have immobile structures in your system. Two, you have non-specific probe-to-medium interactions. And three, you have non-specific probe-to-probe interactions. Non-specific interactions could be electrostatic or chemical interactions. But in this thesis, we will be focusing on the idea that elastic probe-to-probe collisions actually causes anomalous diffusion as well, both subdiffusive and superdiffusive motion. In this thesis, we found that on the global level, scaled Brownian motion, particularly subdiffusion, emerges at highly crowded conditions during short periods of time. But at the local level, we actually see that some of the probes exhibit both superdiffusion and subdiffusion motions despite or even at moderate crowding conditions. So if you want to learn more about my results, then you are welcome to watch my thesis defense this coming June 2, 10:30 a.m. via Zoom. Thank you very much and see you there.